I think the microphones have been off this whole time. Alrighty. If you're watching the recording, sorry about that. The microphone was disconnected.
So did it need an audio recording?
I don't know. Ideally, it wouldn't be able to detect the microphone if it's not there. And it would just use an alternative microphone, so the sound quality might be there, but very bad. Or it might not be there at all. Either way, quick recap of this problem. Arclength formula is square root of r squared plus dr d theta squared. We did an example of the circle. We saw that our arc length by calculation matched our geometric interpretation of the arc length of a circle of radius 1, which we could calculate using the formula of circumference is 2 pi times the radius. Since the radius is 1, this is 2 pi times 1, or 2 pi. In our second example problem, we had something a little harder, where we could graph this cardioid. We saw that the arc length was, again, the square root of r squared plus dr d theta squared. In this case, though, after we did our simplification, we needed to use a trig identity, which we reparameterized to show that 1 plus cosine theta over 2 is equal to cosine squared of theta over 2. And we multiplied both sides by 16 to get that 8 plus 8 cosine theta was 16 cosine squared theta over 2. We substituted that out. Importantly, when we canceled our square root, we needed to make sure we accounted for the absolute value. Otherwise, if we solve that without accounting for the absolute value, we get that our arc length is 0, which is obviously wrong. Once we do that, though, we can see that our arc length is 16 when we finish solving. Alrighty, time for some sequences. So let's start out with what a sequence is. In short, a sequence is just a list of numbers, and the order matters. And sequences are pretty nice because we can do a lot of things with them. So let's start off with just a quick example of what a sequence. I can define a sequence a sub n and say that each term is going to be defined by 1 over n. Of course, I need to say where it starts, so it's going to start at 1. And I could say, well, my first term, when n is equal to 1, would be 1, because that's 1 over 1. My second term, when n is 2, is 1/2. Third term is 1/3, and so on. Well, one thing I can do is I can take the limit of a sequence. If I let n go to infinity, well, this would just be the limit as n goes to infinity of 1 over n, which is just 0. I have 1 over n. So we see that that limit is 0. We can take the limit of a sequence. One common method used to find the limit of a sequence is actually to find the limit of a function that matches it. So if I say that my a sub n is equal to 1 over n, well, then I can come up with kind of like an analogous function. F of x is equal to 1 over x, right? And what I say is if the limit as x goes to infinity of my function is equal to some value L, then what I have is that the limit as n goes to infinity of a sub n is that same limit. One thing to note is this doesn't go the other direction. So if you have a sequence a sub n equals to L, it doesn't necessarily mean that your corresponding function is going to have that same limit. Can you think of an example where that would be the case?
My mind immediately went to convergence and divergence test. That's not this.
That's something else. So we're looking for a sequence that has a limit that exists, but whose corresponding function has a limit that doesn't exist. That might be a nice hint.
Ln doesn't have a limit.
Right, but would the sequence a sub n is equal to natural log of n have a limit either?
No.
No. So what if I had a function whose limit didn't exist because the function looked something like this. Are there any sequences of points on this function that I could take whose limit would exist? Sorry? So you're saying wherever it's 0? I would agree with that. And one thing we could actually see to check is we could define our a sub n to be equal to sine of n pi. Right? Because whenever n is an integer, which it always is in a sequence, we're going to have the sine of some multiple of pi, which is always 0, right? So for all n, this value is 0. So we take the sine of 0, or sorry, yeah. We take 0 over and over and over again, clearly the limit of that sequence is 0. But if we took the corresponding function, well, this is just going to be our sine function, which oscillates between -1 and +1. So it is not going to have a limit. Make sense?
I'm still getting confused about why the other one is considered to have a limit.
This one?
Yeah.
Well, let's start writing out terms. What's our first term?
0.
Okay, what's our second term?
And we're talking about like along the x-axis.
Well, remember with our sequence, we take values of n that are positive integers. So that'll be 1, 2, 3, 4, and so on, right? So if I take the sine of pi, that's 0, right? If I take the sine of 2 pi, that's still 0.
Okay.
Sine of 3 pi is 0, and so on. So all of these terms are 0. So because it's all just a constant 0, we can take the limit of just 0, and that's 0, right? But this function doesn't have a limit. So we could even actually come up with just the points where it's 1 and write a sequence for that and say, well, the limit of that's just 1 because it's just the points where we hit the 1. So yeah, good stuff. But if you can find a function and the function's limit is some number L, then the limit of the sequence corresponding to that function would also be that same. Sound good?
So even in this like odd one-off case, we still consider the limit of sine n pi to be non-existent?
No, in this case we consider it to exist.
Okay, at 0.
Yeah.
Okay.
But it's like this condition showing that your function's limit is L is a sufficient condition to say that your limit of your sequence is also L. You can have this limit without having this precondition, but if you do have this condition, you know what your limit of your sequence is. Sound good?
Yep.
Cool, cool. All right then, find some sequence limits. And we're going to say that n starts at 4 in this one. And I'll give you a few minutes to work through that. do it.
Question you many things.
Cool. Keep it up.
You're supposed to separate it out and get like n minus 1 on the top and bottom. And then not like just n minus 1, but that thing shows up in the top and bottom.
For the first one?
What?
For the first one?
No, for a second.
Oh, I mean, yeah, there are a couple of ways you can show this. Just any way that makes it easy to follow your reasoning is well good.
Just trying to grab onto stuff.
Mhm. You going to move on, or how is it going? Do you get the first one? Could we write it as a corresponding function? So if we wanted to write a function where we just replace all the things with x's, what would that be?
X plus 2 minus 2.
Okay, and we find the limit as x goes to infinity of this. You learned this one, I know.
I mean, you can't find it of that. You have to use lost algebra.
Okay,
Or, well, I guess you don't have to. You can just divide by x, but
Yeah.
same thing either way.
and what do we get?
1.
Right? And because we have a function, we showed that its limit was 1, well then the corresponding sequence must also have limit 1. Make sense? All right, what about the second one? Bit lost on this one? Okay,
I tried to pull a 2 out and then pull an n out of the bottom, but that did not help me at all.
right. So I guess on an intuitive level, which grows faster, 2 to the n or n factorial?
I think it's 2. No, it's in factorial.
Okay, and why do you say that?
Because you're getting bigger and bigger numbers, whereas 2 to the n, you're just continually multiplying 2.
Right, so you've got 2 to the n. Let's just write out the fifth term. We're going to have 2 times 2 times 2 times 2 times 2. That's 2 to the fifth. And on the bottom, we're going to have 5 times 4 times 3 times 2 times 1, right? Okay. Well, what we can kind of do is we can actually just start pairing things up. So let's kind of just make a nice cut and say after our fourth term, I can pair a 1 with 2, a 2 with 2, a 3 with 2, and a 4 with 2. And for everything except this 1 with 2, my denominator has a term that is at least as large as the one on top, right? And in fact, with this 4, I can actually cancel 2 of the 2's, right? So from this point onward, whenever I increase n by 1, I'm actually increasing my denominator, right? So I can kind of actually compare this to if I am just multiplying by bigger and bigger numbers on the denominator, right? And if I keep multiplying by fractions on that are smaller than 1, and I do that infinitely many times, what do I end up at?
0.
Right. So that's kind of an intuitive reasoning for why our limit of 2 to the n over n factorial is equal to 0.
So was that n greater than or equal to 4 on the top 4? Was that supposed to be on this one?
This one?
Yeah.
Well, it's actually because if we plug in n equals 3, we get a 0 on the denominator.
Oh, okay.
Yeah. So remember, with our limits as n goes to infinity, the behavior in the first few terms doesn't actually matter. So because it behaves in one way after we pass 4, that's closer to infinity than anything before it. So we can just kind of treat it how we want once n is bigger than 4.
So,
All right, these limits make sense?
well, I mean, is that the only way to prove the bottom one? Is there no other?
You could probably do it more rigorously using the comparison test. So, for example, I'm just going to say that my limit as n goes to infinity. I'm going to completely ignore the first 3 terms. So I'm going to say for n is bigger than or equal to 4, a sub n, which is equal to 2 to the n over n factorial, is going to be smaller than, or sorry, let's see. Yes, smaller than or equal to 2 to the n over 3 to the n. Because I know that for n bigger than or equal to 4, whatever my n factorial term is contributing, it's going to be bigger than 3, right? So 4 is bigger than 3, 5 is bigger than 3, 6 is bigger than 3. So then the reciprocal would have to be smaller. So 1/4 is smaller than 1/3, 1/5 is smaller than 1/3, and so on. So my 2 to the n over n factorial is smaller than 2 to the n over 3 to the n, which is equal to 2/3 to the n. And we can find the limit of this, right?
Oh,
This is just an exponential. We could just take a function if we wanted. Show that way. Sound good?
yes, sir.
Yeah, so that's a slightly more rigorous way. The intuitive way works fine as well, though. All right. What time is it? 4:39. Okay, we probably need to keep going. We do have a couple of different terminologies. For sequences, we say that a sequence is increasing. If each term is bigger than or equal to the one that came before it. And we say that it's decreasing if we have each term is smaller than the one that came before it. We say it's strictly decreasing if we don't allow this equal sign in it as well. And we say that the sequence is monotonic if it is either increasing or it is decreasing. We also say that a sequence is bounded above or below if we can find a maximum value or a minimum value that it achieves. So I guess one example of that would be if we take 1 over n, we can say that it is bounded above by 1, because no matter what n value you plug in, it's always going to give us a result smaller than 1. We can also say it's bounded below by 0 because we always have a positive value in here. And we also have a really nice theorem that says every bounded and monotonic sequence must converge. Or in other words, it has to have a limit. And this is a really nice and powerful theorem, so just make note of it. We aren't going to do anything with it right now because sequences really are just kind of a lead into series a lot of the time. And series tend to be a lot more exciting. You look skeptical. So let's start off with what a series is. A series is just the sum of all the terms in a sequence. Okay. So for example, if we have, we'll often write it like this using a capital sigma. And you'll often see it written from I is equal.
Greek letters have lowercase.
What?
Greek letters have lowercase. Okay.
Yeah.
So just sorry.
See, now I'm trying to remember some of them. I don't know. I forget. I mean, there's omega and then there's capital omega. That's one of them. Yeah. So if we had a sum, we usually say the first term on the bottom, and we say the next term on top, or the last term on top. And then we can write what exactly we're summing up. So in this case, if we have a sequence a sub n, well then this series would be the sum of all terms in it. So we would start at 1, write a1, then we would add a2, and a3, and so on, until we'd added up every term in the infinite sequence. So let's say if our sequence was, for example, 1 over I, well then that would just be 1 plus 1/2 plus 1/3 plus and so on. Okay, and you might be seeing some problems with this because we're adding up an infinite number of terms, right? We have an infinite number of little bits and we're adding them up. That might also go to infinity, right? So we say that a series converges if it has a finite sum. So if the sum is finite, we have a convergent series. A quick example of something that isn't convergent would be if we just took 1 and summed that up an infinitely many times. Because yep, this is just going to go to infinity, right? So we say that it diverges because it doesn't go to a specific finite number. Importantly, we also say that if it doesn't approach a single number, then it diverges. So if we did 1 minus 1 to the end, this is -1 plus 1 minus 1 plus 1, and so on. And we can say that this sum, depending on where we stop at, I'm sorry, that should be a I. Well, this would actually be -1 if I is odd. Or actually, we should do this as an n. So if our ending index is odd, then we end up with -1, and if our ending index is even, then we end up with a 0. So as n goes to infinity, we can't really take the limit because we come up with 2 values and not just a single unique value. So let's talk really quick about a special type of series. This is called a geometric series. Now, geometric series take very specific forms, and that form they happen to take is the sum A times R. I'm just going to start saying that n is equal to 0 to the n. And if we wrote this out, it would be A plus AR plus AR squared plus AR cubed plus and so on, right? Or we can say that A is the value of our first term, and we call this R value the ratio. Well, it happens to be that we can define the sum of a geometric series depending on what this value of the ratio is. So a geometric series will specifically converge if the absolute value of our ratio is smaller than 1. Oops, not smaller than 0, it's smaller than 1. And it will diverge if the absolute value of the ratio is bigger than or equal to 1. Additionally, if it converges, so if our ratio is smaller than 1, then we can actually say that the sum is equal to our first term divided by 1 minus our ratio. You look a little confused. Oh, this is just S for sum. I know my handwriting is not great. I'll make that more clear. S. All right, so our sum is equal to A over 1 minus 1. So there we go. All righty, so let's say we had a geometric series like this. Well, our first term would be when we plug in n equals 0. We get 2 times 1/3 to the 0th, which is just 2. Well, when we plug in n equals to 1, we get 2 times 1/3 is 2/3. Then we have 2 times 1/3 squared, which is 2/9, and so on, right? So there are a couple of different ways we can find our ratio. Obviously, we already have our first term. We just plug in when n equals 0, that's our start. To find our ratio, the way that I've usually done it is I've just looked at whatever is being raised to the exponent of n. In this case, it's 1/3. But another common way you can find your ratio is by taking any term and dividing it by the term that came before it. So in this case, we could take a sub 1 and divide it by a sub 0. That would get us 2/3 divided by 2, which is equal to 1/3, which is, of course, our ratio. And here we see that our ratio is between -1 and +1, so our series will converge. And additionally, we can say that the sum is going to be equal to our first term, which is 2, divided by 1 minus 1/3, which is 2 over 2/3, which is equal to 3. Right? All righty. Okay, ready to move on? Sounds good. Time for some practice. So find the sum if it converges.
How's it going?
So what I do believe that's a good question. But other than that, there's a lot of question marks.
Right. Let's see what you got.
So, from them, I know that we did the method of his first name, and other good questions. And then for two, I also did something I didn't know if they found that answer.
So A is always your first term. So let's actually take a look at the first one. Your n starts at 1, right? So all we do is we take n for 1, plug it in there, and that'll find us your first term. So what is our first term first? Right? Okay, and how's that going to change your next figure? So fraction division, the easiest way to change flip, right? So multiply by ours. Exactly right.
Oh, that makes sense.
In this case, our ratio is going to be a little off. What's different about this one?
We have the only difference here would be having students.
And we got a 2 in x. What's your second term? So when n is equal to 2. Right, and you have 1/3 cubed, right? So our first term is 1/3. Our second term is 1/3 cubed. Is there a way we can use 2 consecutive terms to find the ratio? Remember, we can take our a sub n plus 1 and divide it by a sub n. So we can take our second term and divide it by our first term.
Okay, so yeah. So that's
So that's a ratio.
that's fine.
What is 1/3 squared? Perfect. Third one.
And this one, so we have
So
we have two additional, so we can just say this is two. Okay, so then,
So what are you calculating now? Okay, are we allowed to calculate the sum? What's the ratio?
the ratio is weird,
Right, so what does that mean?
and it just diverges.
They just diverge.
Okay, so this is.
We'll just do this one. First, we'll run through the previous 3 for the sake of the new who's watching the reviews.
Alrighty, this first one, we just need to find our first term. To find our first term, we plug in n equals 1. We see we have 5 times 1/4, which gets us 5/4. We can also immediately see that our ratio is just going to be 1/4. It's the only thing. It's being raised to a power of exactly n. If you wanted to calculate your second term and do a sub 2 divided by a sub 1, that would also get you your ratio. We'll do that one on the second problem as well, though. So in this case, our sum is equal to a over 1 minus r, so 5/4 over 1 minus 1/4, which is equal to 5/4 over 3/4, which is equal to 5 over 3. Our second problem, we can find our first term by plugging in n equals 1. We have 1/3 to the 2 minus 1 is 1/3. We can also see that our second term would be 1/3 to the 4 minus 1, or 1/3 cubed, which means that a sub 2 divided by a sub 1, which would get us a ratio, is 1/3 cubed divided by 1/3, which is 1/3 squared, or 1/9. And this is equal to our ratio. Now then, our sum is equal to a over 1 minus r, so 1/3 over 1 minus 1/9, which is equal to 1/3 over 8/9, or 1/3 times 9 over 8, which is equal to, times 9 over 8, which is equal to 3/8. Right? Now, some interesting little notes about this one. If I wanted to rewrite it to a form more like in problem 1, what I can do is I can notice that 1/3 to the 2n minus 1 is the same thing as 3 times 1/3 to the 2n, right? Because it's like I multiply by 3 times 1/3, and then my 1/3 gets absorbed into my exponent part. Right? Okay. So now I've got 3 times 1/3 to the 2n, which is the same thing as 3 times 1/3 squared to the n, which is 3 times 1/9 to the n. And in this way I can see, my ratio is 1/9. That's another way of doing it. In this third one, we can immediately see that our ratio is equal to 2. Because 2 is bigger than 1, we can say that it diverges. Alrighty, now this last one. This one is pretty good. We can do the same method we did on number 2, where we just find out what our second term and our first term are. Let's go ahead and do that. We see that our first term, we plug in 1 for n, we get 5 times 1/3 squared is 5 over 9 times, 7 to the 0th is 1, so we're just left with 5 over 9 as our first term. Our second term would be 5 times 1/3 to the 4th times 7, right? So now we do a2 divided by a sub 1, and we get 5 times 1/3 to the 4th times 7 divided by 5 times 1/3 squared. I'm going to turn that 5 over 9 into 5 times 1/3 squared, just so I can easily see what cancels. My 5's cancel. I can cancel a 1/3 squared with 2 of them on top, and I'm left with 1/3 squared times 7, which is 7 over 9 for my ratio. And of course, my sum is just equal to my first term, 5/9, divided by 1 minus 7 over 9. My series is going to converge because 7/9 is smaller than 1. And this is 5/9 divided by 2/9, which is equal to 5/2. Now, if I wanted to make my series look all pretty like I did in question 2, I can do that as well. So I can rewrite 5 times 1/3 to the 2n times 7 to the n minus 1 by doing 5 times 1/3 squared to the n times 1/7 times 7 to the n minus 1. Times 7. So 1/7 times 7 is just 1. So then times 7 to the n minus 1 as well. Right? Do you follow that? Okay. So 1/7 times 7 is just 1, right? And I'm putting this in so I can get this into just an n instead of an n minus 1. So I'm going to absorb this 7 into my 7 to the n minus 1, and that's going to turn into a 7 to the n. Now, I turned my 1/3 to the 2n into a 1/3 squared to the n because I wanted just the exponent of an n. And I can do my 1/3 squared, and that gives me 1/9. And then I'm just going to combine my coefficients, so I have 5 and 1/7, which gives me 5/7. Well, now I can take everything that's to the power of n and put that under 1 power to the n. Or sorry, that should be 1/9 times 7 to the n, which gets me 5/7 times 7/9 to the n. So I can rewrite my sum. Like that. And then it's pretty easy to immediately see what a ratio is. Makes sense? Alrighty. Well, I could give you one more really difficult one if you wanted.
This is on the exam, right?
Geometric series will be on your exam, I believe.
Okay.
Will they make them as hard as this? Maybe, I don't know. It is good to know at least how to find the ratio in the first term. Because if you can find the ratio in the first term of the geometric series, you can find the sum. So whether you do it by manipulating your series to look all pretty, or whether you do it just by plugging in your first, second n values, I don't care. Both are perfectly fine if you're trying to find your series sum. So most people, I think, are going to be a little more comfortable just finding your first and second values and finding the ratio from that. But either way will work. You'll take it?
Yeah.
Sounds good. Alrighty. So fifth practice problem. We should do n equals 1. Go for it.
Two squared times 1/8 is what? So what's the ratio?
All I did is this was like case 5. You got it, so. All right, you ready to go over it? All righty. So our first term, we plug in 1. We get 2 times 1/4 times 2 to the 5th times 1/3, which is equal to, oh boy, 16/3, I believe. We can cancel our 2 and our 1/4 partially. We get 1/2, which cancels with 1/2. So we have 2 to the 4th, which is 16 divided by 3. Okay, our second term is going to be 2 times 1/4 squared times 2 to the 7th times 1/3 squared. Right? Okay, and if we do A2 divided by A1, we have what is essentially 2 times 1/4 squared times 2 to the 7th times 1/3 squared, all over 16 over 3. We can cancel one of our 3's with one of our 1/3s on top. And we also have 16 is 2 to the 4th, so we can cancel 16 with 4 of our 2 to the 7ths. We're left with 2 to the 3rd. Now we've got 2 times 2 to the 3rd is 2 to the 4th. Now 2 to the 4th is 16. 1/4 squared is 1 over 16, so these cancel. And we're left with just 1/3 as our ratio. So our sum is then our first term over 1 minus our ratio, which is 16/3 over 2/3, which is 16/3 times 3/2, which is equal to 8. There you have it. And this one, you could, again, if you really wanted to, manipulate it into a nice, pretty form. I'm not going to do that this time, though. You can work through it if you want. But anyway, good luck, and thank you for coming.